In section 6.2, we're going to be talking about a definition and a theorem that relates the perpendicularity of a line to a plane. The first is the definition. We can define that a line is perpendicular to a plane if it is perpendicular to every one of the lines in the plane that passes through its foot. So if we look at the diagram, we have a plane and we have a line passing through it. Let's call this plane N. If every single line passing through that foot creates a 90-degree angle or is perpendicular, then we know that the line, let's say line T, would then be perpendicular to the plane. The next is theorem 48, and it states if a line is perpendicular to two distinct lines that lie in the plane and passes through its foot, then it is perpendicular to the plane. Well, looking back at the diagram, this should make some sense as well. The only reason why it needs to be perpendicular to only two distinct lines, if we remember in the last section, that two distinct lines determine a plane. So, in fact, that if the line is perpendicular to the lines, then it really is perpendicular to the plane itself. Again, in the first example, we'll be looking at a three-dimensional figure. We're given that AB is perpendicular to BC, AB is perpendicular to BE, BC is congruent to BD, and we need to prove that angle CAB is congruent to angle DAB. We know that AB is perpendicular to BC and AB is perpendicular to BE, but we haven't established that it is perpendicular to BD. So to do that, what we can do is we can say that the line AB is perpendicular to the plane because it's already congruent or perpendicular to two of the lines. And then once it's perpendicular to the plane itself, then we can say it's perpendicular to any line that passes through. So again, we're going to establish perpendicular to the plane based on theorem 48. If a line is perpendicular to two distinct lines that lie in a foot and passes through its foot, then it's perpendicular to the plane. And then we'll say that it's then perpendicular to that other line, DB, that passes through the foot because of the definition of it. Now, why will that kind of help us to get to the proof? Well, we're trying to get angle CAB and angle DAB congruent. And if we look at where those are in the diagram, CAB is here, while DAB is here. And you'll notice they're both a part of triangles. So if I can somehow get those triangles congruent, I'll be able to hopefully prove that the angles are congruent based on CPTC. We already have that line segments CB and line segments DB are congruent. So that's one of the things that will help us. But you'll also know that they share the line AB. So we can now say that AB is congruent to itself based on the reflexive property. And we did just establish that BD is perpendicular. So now what we can do is, since it's perpendicular, we can establish that they are both right angles. And once they're right angles, that they are congruent, because right angles are congruent. And that will lead us to prove that the triangles are congruent. The triangles are congruent based on side, angle, side. And then, since I have the triangles congruent, and angle CAB is congruent to DAB, we can say they're congruent based on CPCTC. In the second example that we're going to look at, we're given another three-dimensional figure, and we're given that B, C, D, and E all lying in plane N. I should label N here. And that line segment AB is perpendicular to the plane N, and BE is a perpendicular bisector to trying to prove that triangle ADC is isosceles. So let's look at where that is. We're most likely going to try to prove that AC is congruent to AD, because those look pretty much similar sizes. Now, to do that, we can try to get the back triangles ABC congruent to triangle ABD, and if those are congruent and we can prove them congruent, then the sides AC would be congruent to AD, which would prove it to be isosceles. So now we need to figure out how to prove those back two triangles congruent. One thing that might help us in this is to know that AB is perpendicular to plane N. And what that would do is it would establish right angles between the lines AB and BD and AB and BC, creating them to be congruent. So we'll start by saying that AB was perpendicular to BD and also BC. Again, that's based on the definition. Once we do that, we can establish that they are right angles and therefore congruent. The other thing that will help us is knowing that BE is a perpendicular bisector to CD. The reason why, if you remember back to the equidistance theorem, is that we know that if something is perpendicular bisector, it creates congruent segments to the endpoints. And BC and BD happen to be going to the endpoints of the segment being bisected. So we can say BC is congruent to BD, again, based on the equidistance theorem. From there, if we look back at the diagram, we have the sides and we have the angles. And again, these angles happen to share line segment AB again. So we can say AB is congruent to itself based on the reflexive property. Therefore, the triangles are congruent based on side, angle, side. And from there, that allows us to say that AC is congruent to AD based on CPCTC, which then establishes triangle ABC to be isosceles.